Dear friends, welcome back to Turbo Missions class of session 6 of module 1. I am Dr. Rudresh BM from Government Engineering College, Krishnarajpete. So in this session, let us know about how the first and second law of thermodynamics apply to turbo machines and how the first law of thermodynamics has been applied to the respective turbo machines, how the second law of thermodynamics apply to turbo machines, static and stagnation states, efficiencies in the turbo machines. Before going for the next slide, I need to introduce some more concepts of turbo machines right now. I said in the beginning of the class and in the beginning of some of the previous sessions, we defined the turbo machines as a system. Thermodynamic properties plays a major role when we are considering such kind of systems also. But how this, when you see this turbo machine as a mechanical system, we need to define as a mechanical engineer the meaning of a system. If you want to apply the first law of thermodynamics and second law of thermodynamics to this particular applications, how it is possible? If I want to apply a first law of thermodynamics or second law of thermodynamics to a turbo machine must be considered as one of the thermodynamic system. It should be considered as a system. That's why while defining a turbo machine, we must define a turbo machine is a system. It's a system where the energy transfer occurs between the fluid and the rotating element, due to which there will be a change in momentum and the pressure. All such kind of things we have already defined in previous sessions. That's why a turbo machine is nothing but it is a system. Okay, so now let us see how effectively the first and the second law of thermodynamics can be applicable to a turbo machines. Let us consider the first law of thermodynamics applied to turbo machines. Dear friends, you are all seeing this particular system that is figure 6.1, a turbo machine as a thermodynamic system. So here I have used this control volume, right? Consider a turbo machine through which a unit mass of fluid is flowing. So we know that the energy conversion process is under steady flow in case of a turbo machines. That is very clear. If you consider a turbo machine as a thermodynamic system with the control volume, right, which is shown in the figure, where the fluid is entering the system at section 1.1 and the fluid is exiting the system at section 2.2. I will consider the section 1.1 as the inlet of the system. I will consider the section 2.2 as the outlet of a turbo machine, and the process of energy conversion within the runner or within the casing, that I will call it as a control volume. We have an axis of rotation of the system. The axis of rotation of the turbo machines with respect to a ground level, I can call that as a respective datum head. Very simple, because all this concept has to be applied to a turbo machines as though we are applying to a respective thermodynamic system. With usual notations, what we can write? Let us consider the two sections, section 1.1 and section 2.2. Right? So at section 1.1 there are important properties are available. That means the pressure at section 1.1, velocity at section 1.1, datum head at section 1.1. Similarly at section 2.2 also we have a pressure, velocity and the datum at the section 2.2 also. Right? So therefore section 1.1 and section 2.2 are the two important sections which could be called as the inlet and the outlet of a respective turbo machines. When a control volume is concerned, that means when a thermodynamic system is concerned, section 1.1 is purely the entry into a control volume, section 2.2 is the exit of that particular control volume. Okay, so let us go into the respective analysis of this particular turbo machines. Let U1 and U2 be the internal energies at inlet and outlet. V1 and V2 are the specific volumes at inlet and outlet. Small v1 and small v2. Capital V1 and capital V2 are the velocity of flow at inlet and outlet. Z1 and Z2 are the datum energies at inlet and outlet. Q and W, that's very very important, the heat and work interaction between the system and the surrounding. So these are all some introduction notes that we have to think about before going for this particular section. Now we have, in case of a turbo machines, energy transfers occurs under a steady flow process Therefore, so we have a beautiful steady flow energy equation between the section 1 as well as section 2. Applying the equations of a steady flow between these two sections, I can write the equations as U1 plus P1 V1 plus V1 square by 2G plus Z into Z1 by GC plus Q is equal to U2 plus P2 V2 plus V2 square by 2G plus Z into Z2 by GC plus W. This is very important. Plus W. In turbo machines, the rate of fluid through the machine is very high and the heat transfer area is very less. Okay. So when you see this particular the concept of turbo machines, okay, the heat transfer area is very less, but the space which is available within the system for the availability of a fluid is large. During that situation, the amount of heat transferred within that particular area is almost negligible. There is no heat transfer from the system and there is no heat transfer into the system. Therefore, the process may be assumed to be adiabatic in nature. So, if there is a process to be adiabatic in nature, then I can say that there is no heat interaction into a system. Therefore, Q is also 0. We have U1 plus P1 V1 is equal to H1, that is the enthalpy at section 1. U2 plus P2 V2 is equal to H2, that is the enthalpy at section 2. Z1 is equal to Z2 because of the same height. Therefore, if you substitute all these conditions in this particular equations, we have H1 plus V1 square by 2GC plus G into Z1 by GC plus 0 is equal to H2 plus V2 square by 2G plus Z into Z2 by GC plus W. When you go to the next concept, here H1 plus V1 square by 2G, that is equal to H2 plus V2 square by 2G plus W. Solve for W in this case. Therefore, W is equal to H1 plus V1 square by 2G minus of H2 plus V2 square by 2G. Where H1 plus V1 square by 2G is equal to H01, which can be called as a stagnation enthalpy. That is the total enthalpy in a system. Similarly, H2 plus V2 square by 2G is equal to H02. Therefore, W is equal to H01 minus H02. So, in this case, how we are defining the concept of thermodynamics? First law of thermodynamics we have applied for this. Once when you apply this first law of thermodynamics, definitely we need to define the type of a turbo machines using the same first law of thermodynamics. From the first law of thermodynamics, I derive the expression W is equal to H01 minus H02. If H01 is greater than H02, that means the energy which is available at the inlet is greater than the energy available at the outlet. It is the case of power developing machines. Example, turbine. If H01 is less than H02, W is negative. That means the energy which is available at the outlet section, if it is less than at the inlet section, I can say it is a power absorbing machines. It is the case of centrifugal pumps and compressors. Therefore, the enthalpy decreases from inlet to outlet in power developing machines, whereas the enthalpy increases from inlet to outlet in case of power absorbing machines. So this concept is very important. In order to know this particular concept of developing a power in a machine or observing a power in a machine, and the heat transfer from the machine or to the system is assumed to be 0, we need to apply the concept of thermodynamics. That is the first law of thermodynamics. Next, my dear friends, I will move to the second law of thermodynamics applied to turbo machines. And see this, the second law of thermodynamics. The second law of thermodynamics state that for a fluid undergoing a reversible adiabatic process, entropy changes to 0. It's a very good statement. I said that the entropy increases from inlet to outlet when the fluid undergoes an adiabatic process. Very important concept. Okay, so due to increase in entropy, what will happen? The power developed by the turbine is less than the ideal work. We have got an actual work. We have got an isentropic work. Isentropic work or an ideal work is one and the same. Right? So whenever there is an increase in entropy, right, naturally what happens? The power developed by the turbine is always less than the ideal work. So when you consider these particular type of the concepts, the work input from the pump always greater than the isentropic work. Right? So these are all some of the important issues we have to consider in this case. From the second law of thermodynamics, what we can write? dq, that is the change in the rate of heat transfer, right? So with respect to an absolute temperature is equal to change in entropy, ds. dq by d, where dq is nothing but it is what you can say, it is the differential heat transfer with respect to an absolute temperature, that is equal to change in entropy. dq by d is equal to ds. This is the standard expression for the second law of thermodynamics. Now once when you apply this, from the first law of thermodynamics, what I can say, m into u2 minus u1 plus q is equal to w. This is the first law of thermodynamics. If m is equal to 1, u2 minus u1 plus q is equal to w. Say for example, in this case, u2 minus u1 is nothing but it is a differential u. du plus dq is equal to dw. Therefore, dq minus dw is equal to du. I can see this dq. This I can write. So from the first expression, dq is equal to t into ds. That is equal to dw plus du. T into ds, dw, that is the flow work, which can write it as p into dv from thermodynamics plus du. We have h is equal to u plus pv. Therefore, you differentiate h. dh is equal to du plus p into dv plus v into dp. Right? So that is the differentiation. Very, very important. Product rule. Therefore, dh is equal to du plus pdv. I can write this pdv plus du as tds plus vdp. So if you consider this with respect to overall temperature, that means the overall system, that is to the stagnation system, dh naught is equal to t into ds plus v naught into dp naught. Therefore, dh naught is nothing but it is the stagnation enthalpies. If dh naught is positive, the power developing machines, whereas if dh naught is negative, it's a power absorbing machines. Okay, so that means mathematically we have modeled by applying the concept of second law of thermodynamics. Once by looking at the respective mathematical modeling of second law of thermodynamics, we are relating the second law of thermodynamics with respect to a turbo machines, whether the machine which could be developing, whether the work is done on the system or the work is done by the system, whether the heat interaction is going to occur between the system and the surrounding. That concept can be clearly known using the concept of second law of thermodynamics as well as the first law of thermodynamics. Next, I am talking about a static and stagnation states. Dear friends, so far even in the previous sessions and even in the last slide also we discussed about a stagnant states or stagnation conditions. Okay, so we have a static state. What is the meaning of a static state and what is the meaning of a stagnation states? This is very, very important. If you consider the static state is that state which refers to those properties such as temperature, pressure, volume, etc., which are measured when the measuring instruments are at rest relative to the flow of the fluid. That means what? See, whenever the measuring instruments, right? That means when you measure some particular type of properties, maybe a temperature, pressure or volume, whatever it may be, right? So when the measuring instruments which are at rest, right, related to a flow of a fluid, that particular state is called a static state of a system. Stagnation state is the final state of a very fictitious, isentropic and work-free process during which the final kinetic and potential energies of the fluid reduces to zero in a steady flow. That is very, very important. When you reach the point where the kinetic and potential energy of the fluid, when they reduces to zero, at that particular state, I can measure the temperature, pressure and the volume. That total work-free process at that particular point is called a stagnation point. The properties which we are going to measure at that particular point is nothing but a stagnation properties, or it can be called as a stagnation state. Okay. Therefore, for a stagnation state, initial state is always the static state. There are different stagnation properties which we can expect in this case. It may be a stagnation enthalpy, it may be a stagnation temperature, it may be a stagnation pressure or stagnation density. Now let us see how do you define this stagnation enthalpy. A stagnation enthalpy is defined as the enthalpy of a gas or a vapor when it is adiabatically deaccelerated to zero velocity. It is very, very important concept, my dear friends. Adiabatically deaccelerated to zero velocity. Right? Zero velocity. That means velocity energy. When the velocity energy has been reduced to zero with no heat transference in a particular system, right? The enthalpy which we are going to measure is nothing but a stagnation enthalpy. Therefore, the stagnation enthalpy H naught is equal to H plus half into V square plus ZZ. This is very, very important concept we have to consider. Stagnation temperature. Similarly, if you define the temperature, it is defined as the temperature of a gas or a vapor when it is adiabatically deaccelerated to zero velocity. If you want to measure any temperature or if you want to measure any of the properties at which the kinetic energy has been reduced to zero adiabatically, those properties are called stagnation properties. We have a stagnation pressure. If we define the stagnation temperature, this can be defined by Cp into T naught is equal to Cp into capital T plus half I to V square. This capital T is nothing but it's a static temperature. T suffix 0 is nothing but a stagnation temperature. This is very very important because the base for the stagnation temperature is always the static temperature. There are two states are available. One is the static state and the other one is the stagnation states, right? So to begin to measure the stagnation properties, we need to have a one initial state. That state is nothing but a static state. Therefore, the static temperature, the static enthalpies and the static pressure are very important properties which we have to measure. Let us think about a stagnation pressure in this case. A stagnation pressure of a gas can be obtained by deaccelerating the respective gas or vapor in an isentropic process which is whose velocity has been reduced to 0. Therefore, the stagnation pressure P naught is equal to P plus half rho V square. Stagnation density. It can be defined as the density of a gas or a vapor at a stagnation conditions of a temperature and a pressure, right? So that means when you define such kind of the properties, it may be an enthalpy, it may be a temperature, it may be a pressure, or it may be a density, right? We must see that the process is always adiabatic at that particular point. At the same time, it has been deaccelerated to 0 velocity. That means the available kinetic energy at that particular point is 0. So that is the stagnation state where we need to measure the respective the properties. It may be an enthalpy, a temperature, and the pressure as well as the density. So these are all some of the stagnation properties and the static properties which we have to define with respect to our thermodynamic fluids. Next is efficiencies in turbo machines. Dear friends, so in this particular system, I will be bringing the concept of efficiencies in a turbo machines. If you see the efficiency of a turbo machines, it's the ratio of the output of the system to its input. But in turbo machines, different efficiencies have to be measured in order to evaluate the overall performance of a respective turbo machines. Why we have to measure the efficiencies in case of a turbo machines? When you see the turbo machine, a turbo machine may be a power developing machine, a turbo machine may be a power absorbing machines. Both for power developing machines we need to supply the energy, both even for even for power absorbing machines we need to supply energy. But how much is the effective about the performance of a turbo machines in utilizing the supplied energy in order to convert that supplied energy into another form of energy? How much amount of the loss that has been incurred in a respective turbo machine system? In order to know all these kinds of situations in each and every stage, for example, we are supplying so much of volume of water, we are supplying so much of power, we are supplying so much of what you can say, that means the high discharge of water. So all such kind of things are resulting in this case, right? Everything is accountable in this case. In order to know the accountability of the energy which is supplied to the turbine system, which is supplied to the turbo machine system, right? In order to account for the respective energy which is available at the respective turbo machine system, we need to define what is the meaning of efficiency. How do you define this efficiency, right? The important efficiencies in turbines and centrifugal pumps are efficiencies in that is we have to define with respect to a turbine as well as a centrifugal pump. Therefore, let us think about the different concepts, the important efficiencies. Okay, fine. So efficiencies in turbo machines. Let us think about a turbine, that is the efficiency in a turbines. First one is the hydraulic efficiency. It's the ratio of power developed by the turbine to the water power available at the inlet of the turbine. We have at the output, we have a power, shaft power we are going to develop with the help of a turbine. With respect to that, we are going to supply an hydraulic energy. Hydraulic energy is the input, shaft power is the output. Its ratio is nothing but our hydraulic efficiency. Volumetric efficiency. So we are supplying so much of volume of water. Okay. So the total volume of water actually striking the runner to the volume of water supplied to the runner. We are supplying so much of amount of water, so much of volume of water to the respective turbo system. But effectively, how much volume of what volume of water actually striking the runner? That ratio is nothing but a volumetric efficiency. Come to the mechanical efficiency. It's the ratio of the shaft power output by the turbine to the power available at the runner of the turbine. Yes or no? Very, very important. So we are supplying some amount of power, mechanical power to the respective turbine in the form of hydraulic energy. When you supply that much amount of hydraulic energy into a system, what much amount of energy is utilized at the respective turbine system in order to have the shaft power energy, in order to have the shaft power at the output of a respective turbo machines. That ratio is nothing but mechanical efficiency. Overall efficiency. When you consider a turbo machine, input to the turbo machine is always the water power. Output from the turbo machine is always the mechanical power, that is the shaft power. The shaft power to the water power, the ratio of shaft power to the water power is nothing but overall efficiencies. So these are all some of the important turbo machines. The mathematical equations for all these kinds of turbo machines will be derived in the coming sessions depending upon the module. Okay, we have a beautiful hydraulic turbines. There we are going to define the respective hydraulic efficiency, the equation for all these kinds of efficiencies. Next is we have got a efficiencies in a pump. We have three efficiencies in case of a pump. One is the manometric efficiency. It is the ratio of manometric head developed by a centrifugal pump to the head imparted by the impeller to the water. Very, very important concept, right? Because if you define a manometric head or if you define a centrifugal pump is a pump which works against a particular head. So the head which could be delivered or the head against which the centrifugal pump is working is nothing but a manometric head. That is the output from a system. With respect to that particular output, what is the head imparted by the impeller to the water? What is the work done by the impeller on water in order to rise that much amount of the head in a system? So in order to prepare this particular turbine, that is the pump system, to work again is the respective hydraulic head. Right? So the output is the manometric head to the work done or the power head imparted by the impeller to the water, that is the input to the pump. So that ratio is always called as the manometric efficiency. We have a mechanical efficiency in this case also. It is the ratio of power delivered by the impeller to the shaft power available at the input shaft. Yes or no? There are two important concepts in this case. Most of the people will get confused. What is the input to the centrifugal pump? The input to the centrifugal pump is the shaft power. Output from the centrifugal pump is always the pressure energy or water power. But we cannot convert shaft power to a water power. But that water power is in the form of an hydraulic power, hydraulic energy or hydraulic pressure, you can say. So like this. So therefore, when you see this particular thing, the power delivered by the impeller to the shaft power available at the input shaft. For a centrifugal pump to drive the impeller of a centrifugal pump, we need an electrical power. Therefore, so that is the power. That's that shaft power of a electrical motor, right? That is the input to the respective hydraulic system, and the power which is delivered by the impeller, right? So that is nothing but our output power in this case. Therefore, the mechanical efficiency is the ratio of power delivered by the impeller to the shaft power available at the input shaft. You see the overall efficiency. You just make out the difference, please. It is the ratio of water power to the shaft power. When a turbine is concerned, it is the ratio of shaft power to the water power. When you consider the centrifugal pump, it is the ratio of water power to the shaft power. Therefore, the inputs with respect to turbo machines are very, very important while defining the overall performance of a respective turbine systems as well as a turbo machine systems. Okay, dear friends. In this session, we discussed about some important things like first and second law of thermodynamics effectively applicable to turbo machines. Secondly, we have the stagnation as well as the static properties related to turbo machines, and after that, what are the different efficiencies in case of turbo machines? How their definition plays a major important role in the field of turbo machines. So all these concepts we discussed in this today's session. So I will be bringing more informations about these particular turbo machines in the future sessions. Thank you.